Now we will find out the value of the drag and the lift coefficient. For this case, the CD value is 0.018, and from the NASA's data, the external data which shows that the CD is 0.012, and this shows that the error is around 50%. We can reduce this error by refining the mesh. Second thing is that we can use the transition model so that the flow can be modeled properly with the laminar zone and the turbulent zone. And with the laminar zone, the drag coefficient will be lower value, because in the turbulent flow the drag is higher and in the laminar flow turbulent is lower. So modeling in this way that the transition of the laminar and turbulent flow should be resolved properly and it should be in accordance with the physics of the problem, we can predict the value of CD very accurately. As far as the value of the lift coefficient is concerned, this value is mostly accurate from the CFD, and it's irrespective of the mesh refinement or the transition model. And since we are solving this case for the 10 degrees of angle of attack, so you have to provide the cos 10 and sin 10 components for the CD. The same we did for the when we were using the monitors, and for the CL we will be providing the minus sin 10 and the plus cos 10. So go to the reports, and from the reports double click on forces, and then click on forces, which is the default option, and provide the components of the 10 degrees sine and cos, and you will get the value of the lift and the drag coefficient. So let me show you on the Fluent. So from the post processing you can go to the reports and forces, or you can just go to the tree outline, double click on the reports, this will open the panel, and from here choose the forces. So for drag coefficient, I will be providing the value of the 10 of the cos theta, put in the x, and then sine of the 10 degrees. Copy and paste this value in the y field and click on the print. So the drag coefficient is 0.018, which is same as we have in the value is same as the 0.018, and the error is still is 50%. And then for the lift coefficient, we'll put the minus sin 10. So first is the sin 10, copy, and in the x field put the cos of 10 and also minus sin, and similarly cos of the 10 for the y field, and click on the print. The lift coefficient is 1.0177, which is almost same, which is 1.018 after round off. So we are getting the values which are on the in the drag coefficient is on the bit higher side, but the CL value, if you compare, if you take the value from the NASA's report, you will notice that the CL value is almost close to the value given by the NASA. So the important thing is that when you are going to find out the value of drag coefficient, which is for the aerofoil cases, this is mostly coming from the skin friction, and there is a very small part which is coming from the pressure drag. It means that you should be resolving the boundary layer properly, and secondly the flow physics should be captured properly. So you will see that in my next course, which is on the aerodynamic modeling of the turbulent flows based on the CFD, where I have explained all the things and the meshing also for the how to get the mesh for the to get the proper value of drag or the accurate value of drag. So you can join that course also. So for the time being, the purpose was that how to find out the value of the drag and the lift coefficient from the Fluent for the case when the angle of attack is the 10 degrees. So you can apply this case with a 0 angle of attack. So you will be putting the cos 0 and the sin 0, and minus sin 0 and the cos 0. And for different angles, maybe for 15, 4, 6, 7, you can put these components and you can get the value of the CD and the CL.